taught you about mosaicing, right? We did a mosaic. Okay. Now we have this huge data. Now what I do, there is one. This is okay. This is the toolbar. This is the ArcHydro toolbar. Okay, this is called ArcHydro toolbar. This is the utility toolbar. This is called as utility toolbar. Utility network analyst toolbar. This toolbar you use for creating a network data from your river network. Okay, this we will use to do all other processes. You can see here network tools here. Okay, you have attribute, you have watership processing, everything is here only. Agreed? Similarly, you will have all the things here also. Yesterday, as I told you, you will have to set these two. Okay. For batch processing, as batch processing is terrain processing workflows. For this, you have to set this set batch target locations. For anything else, you have to set this target locations. For vectors, you have to make a database, create a geodatabase or a person database. For rasters, you just have to show a folder. So everything will go and all the processed data will be stored in that particular thing, the folder. So the first thing you do is see the best process is I think I showed you right yesterday. Where is the flow? This is the flow you need to follow. Okay, you can, if you don't know what to do, where to start, always come here. From fill goes to flow accumulation. Flow accumulation goes to stream definition. From stream definition to stream segmentation. From stream segmentation, you will go to catchment grid delineation. From catchment grid delineation, you will go to catchment polygonization. That is where you get your watershed delineation. You will have the watershed delineated watershed for every stream. For every stream, you will have one watershed. Okay. All the extra things are extra work. I mean, for your necessities, you are doing. But this is the flow, major flow. So how do you do that? Or else, if you don't know this, you can follow here. Okay. First, you come here. You can use any of these symbols. I mean, tools. Okay. Here, the first thing is data manipulation, management, data manipulation. Okay, the part of this is all part of data manipulation. What is okay? Maybe I'll use the whiteboard. Yeah, I have to install whiteboard. I think I will share. Okay, are you able to visit us? See my whiteboard?
No.
Now can you see?
No. Now it's visible.
Give me a second. I'll arrange my things first so that yesterday we talked about sinks. Do you remember? Yes? No.
Yes, sir.
The water sinks.
The depressed areas.
Yes. No, sinks are sudden depression areas, not the depression areas. As in, depressions are part of your terrain, but all of a sudden the terrain diminishes, shows a degraded thing. All of a sudden there is a valley or a peak. That is when you have the problem. Okay, see here. Okay, got it. So now, how do I catch this thing? So here I told you, right? Now what happens is the terrain is like this. Okay. This is the lake. This is a lake. You have a lake here. Okay. So if you have a lake polygon, you will have many lakes. For example, this is a watershed. Okay. You will have a lake here. You will have a lake here. You will have a lake here, or something like that, like for example ponds, like that. Okay. Do I have settings? Yeah, all the settings are clear. Fine, no problem. So these are depressions. Okay. These are depressions. Okay. How do I? Okay. Oh, maybe I can actually do this too. Oh, okay. What is it? Three things, four things. Oh, sorry. One thing. Okay. Anyways, so if you have lakes like this, okay, if you have lakes like that, uh, you will use the lake polygon to fill these ditches so that the surface will look smooth. The surface will look smooth. Because we are not interested in any lakes now. We are only interested in river flow. We will fill this region for a particular height. Okay, so that is what this thing does. That is what this level dem does. Okay, that is what this level dem does. So if you click on that, okay, you have my filled dem. Okay, I have a raw dem. I can also, I mean, I can have this raw dem. This is filled, but I can have a raw dem. I will use lake polygons. All the lakes in the, I mean, if you have to use that lake polygon. And the lake polygon should always have this column, fill elevation. What is the maximum height of a lake? Okay, this is bathymetry. Till what elevation? See, this is the pixel height, this is the pixel height. So this pixel should be in between them like this. So you should have the proper elevation. Till what elevation you have to cover it. So that is these are extra process. These are all extra processes so that you will get a proper flow. Okay. I mean, you don't have to do this. This is just an extra process. So that is called as level dem. Okay. Then comes here you are trying to create a drainage line like.
No, shall I ask one? These things really do exist, or it is happening because of some error or something?
No, these are part of terrain.
Terrain part only, right? Okay.
See this thing, create drainage line, create sink structures. These things will create a polygon for you. They will create a polygon saying that this is the location of the sink. I think I have it. Oh, if I have it, then I will share it. Uh, do I have it? No, I think I deleted that. Yeah. Do I know? I think I deleted them. But or else wait. I think there is one more thing you can try. See ArcHydro. This ArcHydro. See in this thing, there is no output yet. In this thing, sync poly and sync point is there now. I think I will have to open a new ArcMap for you to show all of that. I have to open a new ArcMap. Okay. I will show you how the sync polygon and sync point look. Okay. But this is an extra process you will do, not necessary. This will tell you how the drainage line to the sink happened and the location of the sink. Okay, location of the sink. This is called DEM reconditioning. What is DEM reconditioning? In DEM reconditioning, you will see agree stream is you. This is the real stream network you have. You say that yes, this is the stream network I already have. And you also have the DEM network. Already there is a DEM network that is filled. Okay. You use both of these things to recondition your current DEM. Matlab, for example, you have a 30-meter DEM, but right now you have a 10-meter DEM. So you use these two to recondition this thing such that the output of this fellow will be equal to this stream network. The rest you can actually leave it for default only. Okay. So that is what these two do, and that is the most important thing. Rest are all I don't think this is too much of say it's the same process over and over and again, but for a different purpose. That's all. Sink selection, you can select a particular sink and do evaluation on that. Sink can be a depression, as in a lake. Bathymetry, you can do that also. If you have higher resolution dam like 5 meter, 1 meter, you can do this depression evaluation, sink evaluation. Very high dam network or tin network needs these process. Okay, here you will have fill sinks. Okay, this is where you will have fill sink. You do that, you click that. I have a 30 meter dam data. I will have a deranged polygon if I have. If no, I'll just, this is the output I gave because I already set the variable, the folder where the output has to go. I'll just write the name here, click OK. Okay. The minute or else I can always go here, Arc toolbox. In Arc toolbox, I have terrain processing. In terrain processing, I have fill. Oh, maybe not, maybe here. Right. Where is fill here? Check modeling, DEM manipulation. Here in DEM manipulation, you will have fill sinks. You can do here also. If you click them, same thing. You will give a fill threshold. Once you give fill, I mean, this is optional. You don't have to give. Once you just have to give your normal DEM, and you have to just give output. The system will do, because I already explained you, right, how the system will know where there is depression and where there is sudden increase in slope. The system will correct and it will produce output like this. Array, what is happening to this thing today? Okay. What is happening to this thing today? Zoom delay. Zoom delay. Oh, okay. Okay. So this is my field output. You are not seeing any difference with the DEM data. Yes, you don't see. Okay, maybe these are all depressions. Okay. If you see this area, you see this is filled. I mean the height. Are you seeing my black color shadows here?
Yes.
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 So this area got
Yes.
filled. This area got filled.
And it gets diluted. Yeah, it becomes fair, like much
Dark gray.
lighter shade.
Dark gray to lighter shade, so such
Yes.
that. So now it is balanced. Nicely, it is balanced. Okay, so the river network directly flows into this water body like this. Great. So that is how the fill is done. Once you do the fill, you'll get this kind of output. Okay. After fill, or else you have this thing. The same thing, fill. After this thing, you will have to do something called as flow direction. Okay. Once the fill is done, so now the fill is done like this. The system will now ask, try to do. If I put a droplet here, where will it go? How will it go? Towards what direction it will go? So it will calculate slope. It will calculate aspect. It will calculate the direction of the data of the flow, and then it will give an output. How does the output look?
Looks like
This is how it will look. Okay, you will have to do that here. Flow direction. So if you have sink, you are doing flow direction with sink. Matlab you did not do filling. You can use this flow direction with sink. Okay. But generally we do fill because that is a mandatory process. So you give fill input. You give the filled depth. Okay, then you just give the output location and click enter. Okay, understood? So now because so this is okay. If I zoom into the location here, okay, let us go here. If you see here, you see that the directions are given here. See now it nicely says, okay, the river is flowing this direction. Now it understood, okay, so this is the direction of the flow. So every pixel will generate one direction. The green is one direction. For every direction, it has one color. Okay, it has one color. So that's how it is. Or else maybe we can actually show you the property in the table. Like this. See, yesterday I told you, right? 1, 2, 3, 1, 2, 4, 8, 16, 32, 64, 128. This is the value of the direction. Okay, for example, where is that? I take this thing, I click here. Here the pixel value 16. So north, east, north, northeast, east, south, east, south, uh, southwest, west, northwest. So for every direction, you have one pixel value here, 128, 64, 32. So whatever pixel I click, I think this is the green is in south direction, south or southwest. So let us see. It is 4. So that is it's so that is fourth number is some it is one direction. So based on that, the system calculates the direction like this. Okay. So that is this is called flow direction map. Once this is done, you will do flow accumulation. You will do flow accumulation. Where will you do flow accumulation? This is where you will do flow accumulation. Okay. Here you give flow direction. I mean, you give this value as input, this file as an input. Okay. And you give flow accumulation output. How does the output look? The output will look like this. Now you might actually see, this is a completely black. What is this? But if I zoom into this location here, you see it only identifies the river network, the maximum pixels, the pixels where there is maximum contribution of pixels is rivers, right? So this will calculate the flow accumulation like that nicely. So only rivers will be your output. Only rivers or major streams will be your output. So if I go here, I don't think there is any. It will come as a dark gray. You cannot see it in the data. Maybe I can actually you temperature. This is so bad. Or maybe like that. Oh, maybe I can use what? This thing? Okay. Something like this is already there. I wanted to show you the anyways. So once this is there, I mean, see, if you don't like this way, you can always come here, click graphic view, and then you can arrange. You can just search surface, temperature, slope, red, green. Yeah, give me a second. Here is gray, black, and are you seeing? Yeah, the distance and no aspect, no. Back to bytes. Invert, line. Okay. So that is the river network, anyways. That's much more cleaner. But now this is now okay. This fellow is in raster format. That is uh, pixels. These are all pixels. Now the system will automatically provide you with a tool to convert these pixels. You see the pixels into grid. I mean only river network grid. How do you do that? You do that using the stream definition. Okay. In this stream definition, you give flow accumulation. Okay. Generally, this default value should be fine. What is this number? What is this number here? This number is this. For example, if I go to this pixel, I click on this. The pixel value is 1, 2, 3. Oh, okay. 26 lakhs, 26 lakhs, 26 crores, 21 lakhs, 2,333. So that is the pixel value. What you're saying in the system that any pixel that has more value than this particular number, I want you to convert that into a stream network. Okay. So this is how much? 28 lakhs. So anything more than 28 lakhs, pixel value should be more than 28 lakhs, 15,604. That pixel value, if it is more than that, then please convert that into a river network. Okay, that is what we give. So you have a stream stream definition. You have this output that will look like this. Yeah. So everything else is gone. So the system only stores the data that is only streams. So you will get only streams. So you see, the minute I type all this thing, this is Musi river. So you get all the rivers. Okay, you got all the rivers of the tributaries and streams of the river network. The smaller this value is, the finer your stream network. Okay, if you need even small streams also, you reduce this to that number, you will get extremely detailed stream network. Very detailed, even small streams will be visible like this. Okay, so those pixels will be converted into stream network. Now what happens? These are all in. See, now if I want to create a watershed for this network, what is the mistake? What is the problem is the system will consider. Oh God, if I only can have a contrast. Okay. So basically, so the system will consider the entire river network from starting to the end as one stream network. And you will get a huge Krishna basin. The large Krishna basin is there, no? That is what you will get. But that is not the interest, right? You want the watershed here also. You want the watershed between these 2 points. I mean, if it is that what you want, okay? If it is that is what you want, you do the next pause like this thing. If you want this like this, or where is Krishna shape? This, there is a difference, right? So this is Krishna shape. So if in this particular condition, you will get this kind of watershed without any sub watersheds. Okay. For that purpose, I mean, to divide this thing into this kind of stuff, what we do is we do stream segmentation. Okay. Why this is important is, I mean, how does the system know? How does the system know? Is this particular stream has one similar type of pixel values. For example, if I take this thing, the pixel value of this fellow is around 148, 582. Okay. What is the pixel value of this thing? It's also 145, 48. So based on this network and this junction, okay, based on the junctions, the system will automatically, what is this thing? I think all of this is first order. Yeah. So based on this particular thing, the junctions and everything, the system will generate stream segments like this. Okay. For example, if I do this value here, you see the entire stream network has only one grid. Okay. But if I convert this grid to using, I mean, I use the stream segmentation. I give the stream this file as input stream grid. This is stream grid data. I give this as input like that. Okay. Flow direction as input. Then I give the output location. Rest are all optional. You don't have to do this. Click OK. I will get this kind of data, stream segments. Okay. Maybe I can actually do this much better. Properties. Again, I have to search for God. Where is that? I don't know. What did I find? Maybe let us try this. Okay. So if you see here, hey, where is the is classified? Yeah, this is how we get it. Do we have unique symbols like? Okay, so based on that, you will get different. See, here it is blue, here it is green. So this is what you do your stream segmentation based on the pixel values and the junction. It creates two or more segments. Okay, 2 or more segment data like that, and then it will provide you information for delineation of the watershed. So here you do stream definition. So this is the process you follow. Flow direction, you do fill sinks, flow direction, flow accumulation, stream definition, stream segmentation. Then you do combine, or else you do just do catchment grid delineation. The minute you do catchment grid delineation, okay, you will, how do you do that here? It is, yeah, this thing. You give flow direction and you give linked grid. What is linked grid? You give this segment. You just give that segment data, river segments, and then you give output. The output is ready. Okay, how does the output look? The output will look like this. The output will look like this. Okay. The output will look like this. So for every drainage line, so for every drainage points. Okay. So this is, now you see, this is a stretch of river. There is a joint here. So here there will be 2 points like this. Okay. So this will be one watershed. This will be another sub watershed. Okay. From here to here, it is one watershed. So we can, once you get this, you can always convert this raster to polygon. Or and also you can convert the you can do this thing. Once you do catchment grid delineation, you do catchment polygon processing. So each catchment will convert into a polygon like this. What is that cat poly? So each if I do this, click this just you have to give the earlier thing, like cat delineation, and then it will automatically create cat polygon for you. Okay, cat polygon we will create. So you will have nice polygons also. This will become your base for your next processing. You want to study only on this particular watershed. Why am I taking the entire watershed right now is to tell you I think that I should explain you the most complex thing in this particular process, so that you will be able to do on a much simpler scale. Okay, here I will tell you one small problem that I actually experience. Okay, reason is, see, remove this thing, and okay. You see, this is Nagarjuna Sagar watershed. Okay, Nagarjuna Sagar reservoir. Okay, I personally like the watershed of this river should end here. Okay, and the watershed, this entire reservoir should have one watershed. Okay, the entire reservoir should be inside one watershed. Okay, agreed. But now if you see on this thing, where is that polygon? If you see, or maybe I can actually do this. Yeah, I will do that. Are you able to see? Are you able to see my grid data here? Yes. Okay. How is it clear? Right? Huh? So you see the water body is divided into two watersheds, or in this case, three watersheds. Okay. But what you can do now is you can use this batch point generation, or if you don't like this, you are only interested now. You know that okay, I'm only interested in this particular area. My interested watershed is 1, 2, 3, 4, 5. So I have only 1, 2, 3, 4, 5 or 6 here. My interest is only in this area. So what do? I only select this polygons like this. How do I do? Krishna. Okay, continue. Select. I take this area like this. Okay. I will not take this. Not also this. So this is my interested area. What do? I clip this. I'll select this, export this thing as a shape file. I dissolve this I'll dissolve all the boundaries. I'll make one watershed. Okay. Then I'll clip this watershed area from the entire DEM. Okay. Then I'll reprocess. Once I do reprocessing, what do? I use this. I will not use traditional method. What do? I come here. I'll add points here. Okay, point delineation. You asked me, no, madam. These are called pour points.
Yes, yes. Yesterday you told.
Yeah. So you click here. The most important part of this thing is this thing. You need to create an inlet and outlet. Okay. So the watershed will be coming between the inlet and outlet. For example, you say this is inlet, this is outlet. Okay. The entire watershed will come till here. Or else you don't say inlet, this is outlet, the entire watershed will come till here.
Why those two river stream channel, this is network is not highlighted?
Which one, ma'am?
Which you are pointing now. Just this one.
This is network.
No, but its a color is different. That's why I'm asking. It is not highlighted.
Wait. Wait. I will do pink. Okay. River network is red. Boundary is pink.
Okay, fine. Yeah.
Okay. So now what do? I say, okay, this is my inlet.
But a reservoir need not be confined to one watershed, right? Because reservoir is a man-made structure. So you may be tapping a most what to say feasible point to tap maximum water.
True. That is true. I agree with that. Stop. Okay. Do you want to say no? No. Cancel. See, the minute I added a point here, this watershed became different. Okay, it calculated the watershed till here. Similarly, if I do a point, I can actually add another point. So I can add another point here. Yeah, sync point grid. Click OK. I can actually add a point here. and then the process will happen. It will give me results. Okay, once I click OK, that is what it is. Wait. Now it is stuck. It takes time to do this kind of process. See, that is the outlet. Do you want to say no, no, I don't want to do that. So no, Control Z, Control Z, Control Z. That way you can actually create your own watershed. Okay, your question is why should the water, I mean, reservoir should be in one particular thing. Imagine you are trying to model the flow coming into the reservoir. Okay, now the reservoir, it is in the best interest of the study that the entire reservoir should be in one watershed. Because you will be able to control the parameters of that watershed, saying that this entire watershed, more than 90% of it is water. So the system will, I mean, if you are doing SWAT or you are doing across, the system will not take that into consideration as an for sediment analysis or erosion analysis. The system will not take that watershed into a major consideration. But if you use it, if you put that into a 2 or 3 watersheds, then you will have a lot of problems because you will be adding the excess data. I mean, yeah, it will definitely use the land use as a input, but it is always preferable that you keep the reservoir into one particular thing. That's all.
Sir, I have one doubt, sir. How to identify in the river network which one is the inlet and which one is outlet?
Flow direction.
Give me a second. I just want to know. Here is array. Oh. That is not now I have. So how you say? So you telling me, see, there is nothing called inlet and outlet. Okay. To be frank, for this entire thing, this is the outlet because for my study, this point is where the entire the water from this entire segment, stream segment will end here. Okay, that is my outlet.
Okay.
But this fellow is inlet for this river network.
Oh,
Okay.
yes, sir.
So you need to understand that inlet and outlet are our convenience, for our convenience. I can
Yes,
put this outlet in the middle of the stream and generate my watershed. No problem.
okay.
Doesn't matter. Okay, I'll show you my.
Sure.
What I did was. Okay, let me open. I'll show you my desktop. SM2 or an SM3. Let's try this. I think it will work. Let's see. Okay, in this particular case, what did I do is, see, I did this kind of stuff. Somebody making out of noise. See, the entire, I took the such a way that the entire watershed or Nagarjuna Sagar comes in one particular watershed like this. In certain sense, in some cases, what did I do? I tried to do it. It like this. So this is one particular watershed. This is one particular. The entire Nagarjuna Sagar will come into one particular watershed like that. Okay. 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 This should. So that's how you can do. So outlets and inlets matter only for your understanding. It doesn't really. It's not actually really important. You do it in such a way which will give you the best results. I mean, the results that makes best sense. for your analysis. And scientifically accurate also. So that's how, I mean, in this case, it automatically generated. So it is here in the middle because there is an intersection here. But all you can do is just drag this point here, and then you can regenerate the watershed analysis. You can do your watershed delineation again. You put this point here. One point, there are 2 points, right? You put 1 point here. You drag this point. Okay, you put an extra point somewhere here. So you get one watershed like that. So you can do that manually also. All you have to do is you can add this point delineation, or if you don't like this, you want to have, for example, you want to add multiple inlets and multiple outlets. Okay, you want to add multiple inlets and multiple outlets. You have to use this thing. Patch point, you click point, you if I click OK, I click a point. I click a point somewhere, it will ask me, is it an inlet or an outlet? So you'll say the first point is an inlet. Okay. Then you come here and you put a point here. It will ask, is it an inlet and outlet? You say outlet. You write the name of the point, description of the point. Leave this as default. It will automatically configure. And when you close it, you will have 2 points. And then you delineate using EPA web service or whatever. You delineate based on your analysis, or you can use come here. You can do this catchment grid delineation. It will take these points into consideration, and then it will give you a new watershed. Okay, you will get a intermediate watershed in the middle. So that thing you can do. I mean, see, now I'm telling you, but if you have to do it, you have to do it. That will then only you will understand this thing. Okay. So that is the delineation process, and then you can extract the polygons.
But here, no, wherever we feel like we are assigning inlet and outlet, it may not match with the reality, right?
True. What is reality? Tell me now.
No, reality means, for example, the stream which you are having like pointer now. It may be a topographic elevation somewhere the tributary is starting, the point where arrow is showing. And
Yes.
Depending on the elevation, it flows and joins to some stream next order or the same order down somewhere, because elevation controls the flow. So if we are dividing it like maybe it is convenient for our analysis, but that watershed delineation may not be, because now watershed have a water divide, every watershed.
Yes.
So this what we feel like we are assigning, it may not tally with the real situation, right?
Yes, might not tally. For example, okay, what people like to do generally when they are analyzing river network or river flow or whatever, what they do, they take the monitoring points. You have monitoring points.
Okay.
Yes.
Yeah, like the stream gauge stations or something.
Yes.
Yeah.
That location, for example, there is stream gauge station here.
Okay.
That location they'll take it as an outlet. Okay, why? Because now imagine I have a stream network location here in this point. The entire I don't use any other points, only this point I'm interested in. So the watershed delineation will have all of this thing till here. Now whatever process I do, precipitation, flood, flow, volume of water coming into the river, whatever analysis I do, I will use this data to monitor for the compare.
Yeah. True.
Yes.
True. Yeah.
In that sense, when I delineate here, it gives me the accurate comparison between the observed data and simulated data.
Okay.
Yes. So,
yes.
So is it matching reality? It is not.
It is not. No,
but
no. Yeah,
it is
please.
helping, it is making sense because our analysis needs that.
Yes, exactly.
That is
but actually, for that particular analysis it suits. But in reality, actually, normally we follow the thumb rule, right? When two first order streams join, it is second order. Second and first join, it is remain as second. But two second order joins, it will be third order. Two third order joins only, then it will be fourth order. So that is because
stream model.
Normally we follow like this. So that way it ensures, because we do a lot of water balance studies based on this water.
Yes. True. That is true. That you can actually do when you can do that is in this thing, if you are interested, you have to go here in ArcHydro. spatial analyst,
Okay.
hydrology, there is something called stream order.
Okay. Yeah.
Okay.
Yeah. Exactly. Ha ha ha.
In stream order, you can give input stream raster. You have to give this grid or
Mm-hmm.
segment. You have to give the segment.
Mm-hmm.
Array, okay, maybe I should take it this way. Okay.
Yeah.
Input flow direction. Flow direction. You have to choose. This is output location. You have to choose between whatever stream and straller. So you take the straller. Straller is what you said. Maybe I can actually show you in the internet. Yeah, this is what you said, no? 1 1 becomes 2, 1 2 becomes 2, 1 1
Yeah.
becomes 2, 1 2 again becomes 2 because it's a maximum thing. The 2 2 becomes 3.
Mm-hmm. Yeah.
And this is stream. 1 1 becomes 2, 1 2 becomes 3. This is what normally we use.
Yes. Yes.
There is some special conditions they will use.
Mm-hmm.
Okay. So this is what the order becomes like this. That you can use the same order, and that is what this is. I did that here somewhere. Stream order. Yeah. Remove all this. Yeah. Can I share? Uh, I want to delete the remove, remove. Copy. Where is? Oh, it is here. Uh, why is this not visible? It is there. Oh, it is there. Okay. Properties. Hey, come on. Uh, Give me a second. Why is this not showing me the weighted values? Is this raster? No. Yeah, it is raster. Okay, it is very vector somewhere, right? Network. There. Do you see any recursion, drainage line, drainage point, hydro edge, network? No. Oh, okay, let me see. LDM output, no, not output, ArcHydro layers, stream, how is that can generate it? What is there in that? Uh, yes, this thing is important. Do I have that here? Stream order, yeah, stream order selected, yeah, let's add that. So now I think it will come. Go to properties, go to display, now it is better. Display cat, it is now it comes. Categories, code, there's a temple. I'll use this thing. Okay. So now you see, based on the stream order, even I have allocated the thickness of the stream. Now the first order becomes like that. Totally it becomes the huge river coming here. So this is what stream order do. So now you can actually come here and say, because these two are first stream order number one, I have actually drainage points. We should so. Oh yeah, see the system automatically puts the drainage point at each location, each of the stream order locations automatically. So that is how the system generates also. There is the okay. That is exactly how the system even generates the watershed. For every stream order, it puts one point. So the stream order increases.
Yes, yes.
That. So that's
So
then
that is how the watersheds are like a telescopically watershed, sub watershed,
yes,
micro watershed, like that it comes from, right?
yes. So the system automatically does that. So you don't have to
Mhm.
worry.
I thought it's normally people digitize completely and generate it. System
No,
itself they generate, no?
right
Like,
now they have improved this analysis much better in a much
mm-hmm.
better way. So who is this sir? My network is a big problem. Who? Acha, acha, Japila ma'am. So till here, the river network is there. So we did this. So I choose. So once I converted the where is that? Yeah, I convert this stream definition. I do stream segmentation. Then I do drainage line processing. What does this do? It takes this stream segmented data, okay, and then converts it to the polyline. I mean this thing. Agreed? It converts to a vector. Similarly, there is another thing called drainage point. This is what is these are these points. These points are nothing but drainage points. It automatically gives you the outlet of every watershed. Automatically gives the outlet of the every watershed. Okay, that is what this thing is. These two do the same process. I mean, convert the stream data into polygon or polyline or a vector data. Convert the location of the outlet location of every watershed into a point data like this, so that you will have a point and vector data to visualize and do other processing. Okay, so that is this thing. Where is it? These two are very important. Remember this thing. Once you do this drainage line, you can come down here and use this stream order feature, okay, to generate this kind of data. Once you have installer a stream, you get this output, and based on the grid code, you can actually give this kind of thickness to the river for your visualization purpose. How do I visualize this thing? There is one very useful way of visualizing your watershed. Okay. Okay. I think I will just remove this drainage points for now. Okay. This is my drainage data, watershed. Now this is exactly how my uh, elevation will look. Okay. So if I come here, you will only see white, black, nothing else. There is something, I mean, it has to be, say, whenever you do this process, remember that your data has to be in UTM projection or meters projection. Right now, this is in decimal degrees. So what I did, I converted this thing into 30-meter fill UTM. I converted the 30-meter fill to UTM. Okay, I projected it. Okay, then I did this process. What process? I went here. Uh, Meter. There is hillshade. I did hillshade. This is the hillshade. You can search here. Hillshade. You have to use the spatial analyst hillshade. You have to give the input raster, that is 30-meter fill. Okay. Then output location. All these are default. Click OK. What you get out of that? Once you get, this is the output. Now you see the difference. I hope you are clearly seeing the difference between this and that. Yes? No.
Yes, very much.
Yes.
Amit?
Yes, sir.
Yes. This is called hill shade. Now if I do this kind of process here, I'll put it here. प्रॉपर्टीज में जाओ उसको 50% करो ठीक है Then now I will convert this properties into the symbology stretched surface. Apply. Okay. You see the difference? How it looks? So this is a, for example, now if you use ArcScene for this now, okay, it looks really good when for your presentation. And one more thing is, if you are trying to simulate flood, okay, using the animation, I told you right how to use animation video.
Yes. Yeah.
You create this kind of thing. Start from the below. You don't use that extra. I forgot the name of it. You don't give the elevation data. You started with minus elevation, and for every 10 seconds or 1 second of the video, you start increasing the elevation. Slowly, the water body will fill this thing. I mean, you should have the entire polygon. Okay, you can actually classify this thing as a water body till here. You'll get a thick entire filled water, and slowly you rise. In that sense, you will know, you'll understand. Okay, for this you need to have quantified values. How much rainfall, how much flow will come into river, and how much elevation it will raise. Based on that time step, if you create, you can literally see the flow covering slowly from here, this location, the slowly water will rise till here like this. Slowly water will rise like that. I think I can show that to you tomorrow. I'll create that video for you and I'll show that. Okay, how to do. Okay, from here it will come here. It will come here. It will come here. Like that, you'll generate. Okay, this is the height at which the water will stop if this much rainfall is there or this much flow is coming into the water body. So you know the inundation. Where is the inundation happening and all. Okay, that
This,
is
can you
simulation.
show it for the entire basin at least? This one with the hillshade one. Just.
Yeah, this thing is there, no madam. This is how it initiate will look.
Mm-hmm.
Example, if I take this push. Okay, if I go here like this. See, if you see this particular thing here, array, I have to choose black again. You see, we mentioned yesterday, this is the boundary where the water droplet either goes this way or this way. So that is the boundary of the watershed.
That's
Amit,
water divide we say, no?
yes,
That.
yes. Amit, are you understanding
Yes, sir,
this
very much.
concept? Because ma'am is already well versed
Yes.
in this concept. It is you need to understand.
Not
Okay.
well versed.
Yes, sir, I'm getting.
Okay.
So this is how you generate the data. So now I like this area because there is, if you see here, there is mountains also. There is
Yeah,
turf also.
this no, it has basaltic terrain, flow basalt terrains and all. It's part of Deccan, no?
I have no idea what is the
Yeah, yeah.
terminology.
No, what you
But
are seeing here, like below, like layered structures, no? Here, this
yeah,
and all,
yeah. This thing,
basalt
this thing.
flows. Here, down, this here and all. This is basaltic flows. Here.
Oh, okay.
Hmm.
Actually, to be frank, I actually selected the part of it. If we actually have, oh, it is here. I already have it. Anyways, if we
Now,
have,
actually, my area of interest is also in Krishna Basin, Lower Bhima.
oh,
Yeah, I work in that
then
area. It
actually
covers.
this is
Hmm.
helping you a lot then.
Yeah, that's what. It
Matlab,
happens.
I think you are interested in this particular region.
Yes. It starts from Solapur. It ends near to Raichur. Actually, it enters into Telangana.
That's what it
But
is
you're
here,
telling
no?
the Musi and everything. No, it is in that Mehboob Nagar and
Oh, so
Rangareddy district. Huh.
you are in the middle lower part of the Krishna Basin, like
Yes. That is Lower Bhima. Mm.
yeah, yeah. So that is what I think. That is okay. I think this is very useful for me.
Yeah, very useful.
So, so in that sense, so you can do this kind of thing for if
Mm.
you want to represent this thing as a map.
Okay.
Okay, you can do. See now you will have a very nice grid like this. So you can make a map. But if say suppose you want to create a density map, which area has a huge amount of network, water network. What you can do, you can create a map like this. Where did I go? This here. No, no. This is here. No. Hey, where did I put that? Where is the IDW and freaking and all? Okay. Maybe I'll basically I need to go back again to search for it. Where is that? Where is that? Where did I do? Sorry? Oh, okay. It's here. Or maybe it is in layers. Yeah. I mean, this is only for example purpose only. You can do it much better way. But just example. So I created a density map where there is huge congregation of river network. Wherever there is lot of stream network joining together, I created a density map out of it. Like this area has huge river network flow, a lot of river network. This area has a lot of river network. This area has this area also has a lot of river network. But this area is completely one stretch of flow. So in this, that's how I did it. I mean, oh no, that is so that's how I created density map. And one more thing, this tweaking method. Okay, this is called interpolation. We do interpolation of the data. So this is how the interpolate this is one type of interpolation. The other one is another type of. Yeah, this is one type of interpolation. This is one type of interpolation. Now, how did I get to this kind of data sets? What did I do? I have this river network. Okay, I have stream order. Fine. I calculated the length of this stream. Okay. What I did, I just went to attribute table. I calculated the length. Agreed. Then what did I do? I generated a grid like this. How did I do this grid? I think you know how to calculate length already. I don't have to discuss. But this particular thing is you have to do it this way. Grid index feature. Grid index feature. What does it do? It creates this particular grid around the given input. So I want, this is my input. I want a grid like this around my input. What does it do? It takes the input. This is my input. Because this is in my decimal degrees, it wants the pixel size. 1 degree versus 1 degree. This is 1 degree versus 1 degree. I can make it to 0.25 also. I'll show you how it looks. Okay, 0.25. Okay, if I do this, what is the output data? Add, go back, OTM, ArcHydro. You see, that's how I get. Or else if I don't want this for this feature, what do? I create the same thing for entire Krishna basin. I go for entire Krishna shape and I use the entire Krishna shape for, okay, maybe I'll do that for you now. Add attribute index name. I will not take this, I'll remove this thing, I'll add entire Krishna shape. Okay. Close this thing, add this thing. That. Okay. Now you understand how did I get the grid? This is how I got the grid. Okay. Once I get the grid, my entire concentration right now is to send this particular length or whatever parameter I have, density or order, stream order, or whatever parameter I'm interested in,
On
flow.
which basis those grids are formed?
I just explained, madam.
Maybe I missed it. Just like what is the basis behind that?
Yeah.
Like,
See, I take this shapefile, Krishna shapefile. Okay.
okay.
Now I want to create a grid around the shapefile like this.
Okay.
So I give the input as shapefile and I specify the pixel value.
Okay. Yeah. Yes. Yes. Okay.
This is in
Fine.
decimal degrees, but if it is in UTM, you
2
will
meters.
make it 30 meters, 20 meters, something like that.
Okay.
Okay, you get a grid like this.
Okay.
Agreed? Once you get a grid like this, you can use the join feature.
Okay.
Join feature to whatever parameter you want to join, you can join. Before joining, you have to say what happens is before joining. Yeah, actually, you can actually have to create an intersection between these two. Or if you're not interested in intersection, matlab, what you're trying to do is intersection mein, wherever this line is there, only those pixels will be selected. Understood? Wherever the line is going, so this pixel will be selected, this pixel will be selected, this pixel will be selected, pixel will be selected, but these three pixels will not be selected. Selected matlab the data will not transfer into the pixels. It will get null values like this.
That is something like active and passive cells, something like that. Right?
Like this. When I do intersection between river network and the grid, wherever the grid network has the same value. So what did I use is I use page numbers as my cross verification column. You remember how to do joins, right? You need a same columns. Like if you have districts, you need to have districts. If you have countries, you need to have countries between the two shape files. Okay, the same thing has to be there. Okay, so once you have the same thing, it links. So it is the same thing, right? Page number is 2, 3 here. The page number is 3 here somewhere. There is page number here. Yeah, page number is 3. So page number matches. The data is input. Rest all is null, 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 null. And then I use the shape length as my classification product. The term which gives me classification. For that classification, I use this. Okay, once I did the intersection, I use this intersection here, intersection. I selected the this thing. I selected the grid medium like that, or maybe yeah, that generated the intersection decimal degrees. These are all basic. I already taught you how to do this intersection. So you do this thing, you'll get an intersection. Let me show you intersection. Yeah. I think I should have it here. I think I should remove this. String grid intersection. This is the intersection data. Okay. This is the intersection data. Now, if I see open the attribute table, I have the intersection between these two files. You have this page name from the grid. Okay, I'll show you the attribute tables of the page name also. See, when you generate a grid like that, okay, two things what you have is a page name. What is a page name? Each box is one page. This row, maybe if I select this thing, sorry, selecting. Maybe this is the wrong rows. I think I should. Oh yeah. A2 I select. Is it selecting here? A2, A3. One page. B1, B2, B3, B4, B5, B6, B7, B8. Can you tell me where do you see this kind of page numbers and all? Because you people are geography, sorry, geology, you must be knowing pretty well.
In toposits.
Well, very nice. Also in Atlas, also in search criteria. Wherever you want to search criteria, you'll have this page numbers. In that page number, what is there? The data will be here. If you say I want particular location, the system will see which page number the location is there, and will give you that location only for searching criteria. Okay. So that is why people create this kind of grid. So now I have this thing. I intersected the line with the grid. What do I have? I got this kind of result. I have the line. I have the line data. I have the line network data. This is all line network from node to node. I actually have to explain this thing. When the river network is being generated, okay, you will always have this from node to, I mean, even if you don't have this kind of data, you will have to generate it. Automatically you can do it, okay, from node to node, grid code, hydro ID, all that you can do it from here. If you don't have this kind of data, you can go to this attribute table under ArcHydro toolbar. You can actually do assign hydro ID, assign unique ID, assign watershed ID. You can also create from node to to node, generate from node to to node here. Basically, this is all simple step. You just have to select this river network, click OK, that's all. The system will automatically generate this kind of toolbars for you. You don't have to work anything. Okay. And then you'll get the columns like that, and you can use that after you generate all of that. You can use this thing to merge, I mean, do the intersection between this grid file and the river file. You will get this information. For every river network, wherever the river network is there, the grid, if it overlaps, the grid will be selected into the intersection. Okay, B1. This is B1. So this is the B1 grid. Page number. Yeah, this page name. This is page number. This is shape length of the shape. I have this parameter here. I use this parameter to classify the data, to generate a grid like this. Grid like this. Okay, I did the intersection here. I did an intersection. I have this data like this shape length. I use this shape length to classify the data like this. Okay, once I classify, now I know what is the most important parameter. Now, after classifying, I will generate the centroid of these points. For every block, I will create a centroid. In your network analysis, I taught you, right? They have the demand points. How did they create demand points? They will have a administration boundary like this. Okay. They will have a grid, they will have a property like that. Okay. They will have a property like number of people living in the grid. 35,000, 76, 767 people are living in this particular administration boundary. Okay. They want to convert it into a demand point. What do? They convert this into a centroid. Like how do they do that? Is from like this. Feature to point. They use this data set. They give this feature. They'll provide the output data, output location, and they get grid point like this. Uh, uh, where was that? Maybe such hard to see it. Okay. See, I generally forget where I put my नहीं ये क्या है नहीं ये नहीं ये हाँ ये okay so using that I get a point like this okay what does a point have the point have all the attributes of the polygon okay the point has all the attributes of the polygon this is exactly how you will also generate point data for your rainfall, for your temperature, for your solar radiation, humidity, whatever you have, you will generate like this only. You have a grid data. In that grid data, you will input point, you will input columns like this. You will give columns like this. For every location, you will give different. For example, you have this different columns, right? You will give temperature, rainfall, distance, number of people living, for number when male versus female. You can give it is n number. You can do number of data you can give. Once you give this data set, okay, now you have points. Okay, now you need to convert these points into raster for generating this type of data. This type of density data, if you're trying to do, you have to convert that point data into raster. You might ask me,
So we
sir.
have classified that for doing this density analysis.
Yes, we did that for this thing. But you might ask me, sir, why I need to do? I already have this grid.
Yes,
I
sir,
already
that
have this
also.
grid. Why did I do? Because this is discrete. You see, there are boundaries. The boundaries. You cannot specify anything in real world like this. It is not possible. Okay. Can you say okay? यहाँ पे बारिश हो रही है यहाँ पे बारिश नहीं हो रही यहाँ पे 40 डिग्री है यहाँ पे 30 डिग्री ऐसा नहीं होता ना it is a continuous process it is increasing or decreasing continuously for that purpose you need raster data because raster is a continuous format it is a continuous format it is not a discrete format like a vector data so for that reason you use some process called as interpolation you use this data set uh, in this thing, you have 3 or 4 options. You have IDW, kriging, natural neighbor, spline. Okay, the process is same. You double click here, you give the input. Okay, you specify the Z value. If you have height, you specify the Z value, or else you just specify the raster and you give the pixel size 30 meters, 20 meters, 50 meters, whatever the pixel size you want, you give. Maybe I'll just show you that. Joints and this is now because of this the decimal degrees, it is 0.02. You can change it to 1 to whatever you want. Okay, and then leave everything as default, click OK. You'll get the output. You'll get the output like this. Right now, I tried 2 things. That is, one is this thing, one is kriging. I can actually try showing you the spline also if you want. Spline is also one thing that is very important. Same process, you do that. Page number, no, I want to use length as my classification data. Length as my classification data. Spline type is regularized. You can choose any of this thing. Just give output as spline. Okay. Rows. data, spline, yes. Then you classify it. Apply, okay. So that is spline. Okay. Each one has its own assumptions and statistical approximations to generate this kind of interpolation data. Okay. For example, in certain applications, you need to develop rainfall approximations like this. You have a grid data for entire Krishna basin. I think I can show that to you. I think I have that data with me. Wait. So that you will understand what is the significance of this thing. Here is the layout of central location. No. Different shapes. What is sprite? Canals. No. Maybe I have this in P, F. Maybe I think I have it here. Weather data. MD. MD 0.2. So do I have location data here? Yeah. This is the location for every grid point for entire India. You need to generate every day for every day you are trying to generate the raster data so that you can use that data to see the change happening in the rainfall pattern or temperature pattern. You need to actually develop raster for every day for entire 1 year, 2 year, 3 year, 10 year, decade like that, and then do the comparison analysis. Then you'll understand where is the maximum interaction happening. Where is the location where the highest rainfall is happening? Where is the location where the lowest rainfall is happening? Drought regions, all you can find out using the interpolation techniques. Okay, you can use the interpolation techniques for doing that process. Now, oh yeah, we have 10 minutes. Now, I wanted to actually teach you, show you the network analysis toolbar. For example, I think yeah. Okay. See, you can actually use either this tool here, flow. You can display flow arrows. Okay. This fellow shows the direction of flow from the stream network. It shows the direction of the flow. You can choose this thing. Display arrow of you can just choose, ignore that, the direction flow goes. Okay. But if you are interested in for more things like this, you can actually come here, like how you do network analysis. You can put a flag here. Hey, what happened? Where is downstream? Okay. Oh yeah.
That is slower beamer, what you are seeing, no? That.
Yeah. So this is what it is. So you can use the same thing. See, you can put the barriers. You can put the sorry. You do that, and then you solve it. You have you don't have the I don't have the vector functions. I mean the raster data. I mean the watershed here, but you can do the same thing. Find the path upstream. You can do all kind of sauce. I mean, right now it is not working because there is no data inside this thing. But if I click this thing, I say downstream or I say find upstream accumulation or trace upstream. I can always get the all these things will be selected. Or if you want to say, see, I want to get associated watershed for this thing, it will automatically get selected for you. Or you can also, if you have flow data, if you have find path, common ancestors. If you want to analyze this stream, you want to have common ancestors, you will get this entire thing and this thing also. Okay, like that also you can do. Find disconnected. You can do any of this process. I mean, I wanted to try this thing. This is the same thing. You have to just go here. What happened to this thing now? Oh, okay.
But you are showing now somewhere how the rainfall data can be clubbed with the stream analysis.
That was in the interpolation.
Only for interpolation. Okay.
Yeah, you can club the data for different analysis also. You can use the data for different network. If you have this kind of stuff,
Yeah.
This is a location of each grid. Wait, I think I have another point here for you. Is this the point? Yeah, this is 0.25 degree of every. I mean, what did they do? They are monitoring stations randomly, right, throughout the India. They generate data, they interpolate the data, they give a grid data. This is the location of each grid. From
they
this
do
grid,
with Ascent polygon method, no, or fishnet.
Yes. This, and then you use this data because the giving raster is very heavy.
Okay.
So they transport the data and they send the data in this format, grid GRD format. From GRD format, you have to extract and convert it into your processing process. I mean, data that can be processed. So you can use this location to find out where is the interested location. Then we can use that to create a raster for
and they have a time series data also for all these.
Yes.
Where it is? Is it in public like domain? You can where?
Yeah, it is. I'll show you.
Okay. If it is an open domain, it would be. IMDs, okay, site.
You can download rainfall here, temperature here for 1901 to 2020. You can download. Once you download, it will be like GRD format, binary file. You have to extract the data. I mean, because you have CSE background, it will be like a cakewalk for you. So once you extract the files, you will have a you will have a file like this, and then you generate a file like this. Okay. Now here, for every grid, for every location, I have from 1901 to 2019, I have rainfall, daily rainfall. This I used to generate for SWOT analysis. I used for also for creating raster temporal raster data for different analysis. I used for that also you can use temporal. I mean, you can use interpolation. What I taught you right now.
Okay.
For displaying purpose. In this particular case study, you can use that. You can use this kind of points to create a density map, create a flow map, create a displaying where the river network is more or less, flow is more or flow is less. Based on your interest, you can create maps using interpolation. You can also, if for example, you have 60,000 points of elevation like this.
Yeah.
Okay. You use this interpolation technique to make a DEM data. Like I have a DEM data right now. You can create the point digital elevation data for this for your analysis. You can use that data for processing your other, extension. Okay. For that also interpolation is very useful. So, but I wanted to show you this thing. Maybe I'll do this again tomorrow, but I'll just show you this particular thing now. So this forms a network. So where you want to go is for here is a network here. create a hydro network generation. You just create a network data. You have the drainage line, you have the catchment, that's polygon data, wherever watershed delineated data. You have the drainage point data. This is the name of your network. This will be output. ArcHydro and ArcHydro junction is the output. Okay, you will get this kind of result. In some cases, you don't want to do that. You can actually use this kind of thing. You know this thing. You have this kind of thing. This is truly network. For example, where do you use this? Storm water prediction, because this is network, direct connection. This is the node, this is the network. Okay. You can use, if you have flow rate, how much water is coming here. Can the channel handle it or not? All that process you can do. Storm water analysis you can do. Flood analysis. If I have this much water, can I connect these two things? The water can flow here or not? That analysis you can do. That kind of all kind of analysis you can do this with this. Same thing. I mean, now I cannot teach you again the network analysis. You use this data, create your network data. I already told you how to create a network data. Give it a flow rate as your cost analysis and run your analysis. Solve the issue. You will get an output. So this is how the network is used in the ArcHydro.
Yes, if by chance anywhere, can we quantify that flow also? Is it possible?
Now I have not tried it, madam, till now. So I have no idea.
Okay.
But yes, I think quantify. What is quantify? I mean, how do you want to talk?
Like you say, no, we have a lot of inlet. Final one outlet point will be there for your Krishna basin also somewhere.
Oh, that you can do. Yes, that you can do. Because see, that is the traffic data. Okay, network analysis means it is traffic data.
Okay.
For every hour, you create a traffic flow. Okay, 1 hour for every 5 minutes, this much water enters. What is the output at this particular location? You have a time data, you have a traffic data, you have an output. Finish.
Okay.
So I think that is a practical for you. You have to do that analysis.
Okay.
Okay. So anything else I can do for you in this process? I think now I have completed my ArcHydro. Maybe tomorrow I'll show a part of this thing again, but that's it.
Yeah.
Okay. So tomorrow, if there is no other doubt, then I will do is I will concentrate on these particular tools: spatial statistics, spatial analyst. Okay. I might actually I will not cover all of these things in my practical studies, but mostly these things will be coming, especially raster creation, raster interpolation we did already, hydrology we did, density we did, extraction anyways we have been doing it. Reclassification is what we did, classification. Surface is what segmentation and classification, all these things come under the classification process. Math algebra is what I will teach you, what you can do with these things. Okay, local, zonal, we have global here, focal, overlay functions. Yeah, we will do these things. Statistics may we can do some of these things. Okay, rendering, utilities are very important. Then analyzing patterns also we can do. I mean, I can cover most of it because these are, I mean, they are not part of your syllabus, but I will do it just as
mapping clusters.
This thing, yeah, mapping clusters is what you have, hotspot analysis. We did this already. Where did we do? Can you tell me? When we did the network analysis, we also did in Kerala district map. You have population.
Yes. Yeah, population.
Yes, we did group. No, I don't think I did group analysis. But I think I did clustering. Clustering and hotspot are both same.
Yes, both we did with histograms and points
yes. So yeah, mostly. I mean, I've been covering most of it already. But this week, I will only focus on this thing so that we'll complete this thing. Okay. So that is that. If you have any doubts on hydrology or anything like this, please contact me. No problem. Amit, it is you need to understand most of this thing. Okay?
Yes, sir.
So I will stop the recording right now. Recording, there is nobody. Anyways, stop recording.